Howdy, this is your friendly neighborhood physics teacher here, and these are some old free response questions that I found that I thought would be good to go over so you can kind of see how energy reacts with momentum. Again, I keep harping on this. I really do think that one of your free responses will be an energy question. So I'm trying to find as many energy questions that can relate to different things. So the first, I did the energy free response questions, and you can see how that related back to 1D motion on one of them. And then I think it did relate to, and then the momentum free response did relate back to energy a little bit. So this one is going to relate heavily on Newton's third law and the conservation of momentum. And and we'll see how different things react. So right here, so the figure shows part of a system consisting of a block at the top of an inclined plane that rests on a table, which is located on Earth. The block and plane are at rest when the block is released. Trial 1. There is no friction between the block and the plane or between the plane and the table. So friction does not exist in this world for trial 1. In trial 2, the plane is fixed to the table, so it cannot move, but there is still no friction between the block and the plane. Indicate whether the speed of the block related to the table when the block reaches the bottom of the plane is greater in trial 1 or trial 2. Justify your answer. And make sure it's a clear, coherent, paragraph length explanation. Now remember, one of your free responses is going to be a paragraph length explanation. So the first thing is, so we have trial 1, which we'll use the picture, and we'll have trial 2, which I'll redraw so we can kind of play with it here. So trial 1, there's absolutely no friction anywhere. So there's no friction anywhere. The plane, the little triangle can move, the block can move. So for trial 1, there's a couple of things we have to think about. We have Newton's third law here. Newton's third law. So remember, it's Newton's third law is for every action, there's an equal and opposite reaction. So as the block is going down, it's actually putting a force, right? I mean, because there's that force of gravity there. So it's actually putting a force on the table. So as it's moving, or on the plane. So as the block is moving down, the plane's actually moving in that direction. So since the block is moving, it's actually putting a force on the plane. And so we have to remember that there is conservation of momentum. So both objects have mass, and both objects have a velocity now. So basically, we have to think that the mass of the block times the velocity of the block has to equal the mass of the plane times the velocity of the plane. So both of those have to play into consideration. Another thing we have to think about is the conservation of energy. So the conservation of energy. So at the top, before it moves, when it's at rest, we just have gravitational potential. So at the top, we just have gravitational potential. But as the block is sliding down, we have two objects that start moving. So that gravitational potential gets converted into kinetic energy for the block plus the kinetic energy for the plane. So that energy is being split between two different types of kinetic energy once the block gets down. And so this should be at the bottom. So it does get converted into two different. Now, for our second trial, the plane is not able to move. It is connected to the thing. So the block is still moving down, but even though there is still a force pushing down on the plane, the plane is not able to move because it's attached. So there's no really need for Newton's laws there. And there's no need for conservation of momentum because we don't have two things kind of pushing off of each other. But we still have conservation of energy. So we still have the conservation of energy. So again, we still have gravitational potential at the top, but in this case, it's completely getting converted into your kinetic energy of the block at the bottom. So it's only getting converted to the block. So therefore, and it's asking, so if we go back here, it says indicate whether the speed of the block relative to the table when the block reaches the bottom. So we're looking for the speed of the block relative to the table. So the table's not moving at all. So it kind of gives you like a frame of reference there. Well, trial 1 is going to end up being slower. So trial 1, your velocity of trial 1 is going to end up being less than your trial 2. And the reason is because in trial 1, it's having to share that potential energy with the plane because the plane's also moving. So that's kind of like a breakdown, and you would want to make that into a cohesive sentence. So I would do something like this. Sit there and make an outline, kind of like how we did here, and then put that into words. So that would be my suggestion. Okay. So I know I usually make like question 1 and 2 videos. Well, that question 1 was just a little example. I'll just go ahead and go into question 2. So question 2 states we have 2 blocks of A and B of equal mass, M, are on a frictionless track as shown in the figure above. Block A, initially moving at speed VI, or just V1, has a perfectly elastic collision with block B. So that means it hits and bounces off. And if they're the same mass, you know that it's going to be a perfect transition. A will hit B, B will move, A will stay. Because it's a perfect elastic collision and they're the same mass. So it's just like a perfect little bounce and go. So block B has a speed of VI immediately after the collision. And okay, stated that, even though you should have already known that. And then it travels around a circular loop with radius R, where R is much greater than the size of the block. The speed of block B at the top of the loop is V top. Block B then slides up the ramp until it comes momentarily at rest at the height h above the floor. So derive an equation for height. So we are needing to solve for height, and we can use terms of m, r, v top, and g. So when you're looking at these problems, first thing is try energy, because energy really are these more simple equations than like 1D motion or anything like that. So even though there is a little bit of momentum here, it's just telling you it's a perfect little transfer. It's just trying to throw you off to make you focus on momentum, but this really is an energy problem. So let's think about what types of energy we have going on here. So right here, as soon as it hits, we have kinetic. At the very, very top, because it says it comes to a rest, we have, so this would be 100% kinetic because it's at the ground level. This would end up being 100% potential because it comes to a rest. Now, it is saying we have to use V top, so let's look at V top. V top, there'll be some percentage of potential and kinetic because it is at some height, which we can figure out. So if that's a radius, so the height is actually going to end up being 2r, because that's the diameter, right? And some kinetic, and the kinetic would just be using the velocity at the top. So those, because we're assuming because it's frictionless, so the track's frictionless, so we don't have any loss of energy, so we can just look at our conservation of energy. So we have kinetic energy at the bottom equals our potential, we'll put C for circle, plus our kinetic at our circle equals our gravitation at the top. And then we can just kind of plug in things from there. So we know it's 1/2. It says that the mass is just m, And at the bottom, our velocity is going to be V1 equals, so it'd be mass, gravity, and our height in this case would be 2r plus 1/2 m v top squared equals mg, and the height is just h. And these are the terms we needed it. So do we see vi in the terms at all? So we can actually, and there's two equal signs, we don't need it all. So we actually can't use that because it doesn't want it in terms of vi, it wants it in terms of v top. So we can only use this part of the equation. We can't use that at all. So it is making it a little bit longer. We see that our masses cancel. So we're left with G2R plus 1/2 V top squared equals GH. We're actually solving for H. So we can go ahead and divide by G by both sides to get H by itself. Put it over here real quick. So H equals G2R plus 1/2 V top squared all over G. You can leave your answer there, but hopefully you can see you can substitute a little, not substitute, you can cancel out your G. You just have to know that that G is actually basically what's happening here is you're dividing both sides by G, and so it makes this G cancel, so you get that the H equals 2R plus V top squared over 2G, because it's 1/2, I just brought the 2 down. So that would be our answer. And I don't know why our 2R looks funky there. There, make it a little bit the same. So I know everyone wants to go like potential at the top equals your kinetic at the bottom, but it didn't want it in VI mode. It didn't want that at all. It wanted it in V top. So you had to see about that it had potential and kinetic there. So hopefully that kind of makes some sense. So part B states that suppose that the speed of VI of block was doubled. Will that cause the height of the block B to be greater, less than, or equal to 2h? So now, thank goodness, now we can use the kinetic at the bottom equals our potential at the top, because we're just worrying about our VI. So let's just focus on this part real quick. So I just plugged in VI, MG, H, because that's our top. Our masses cancel. So we're left with 1/2 V1 squared equals GH. Again, we're looking for 8. We're just focusing on H. So we're going to go ahead and get H by itself. So we get that H equals V1, 2 over 2G. Again, since it's 1/2, I just brought the 2 down just to make it a little bit simpler. So that is what our H equals. But we're going to have a new H. So we're just going to call it like H prime or something, just to simplify that it's a new H. And this new H, we're doubling our velocity. Now, don't forget about the squared. This is where everyone kind of messes up. That squared has to go to the 2 and the V. So our H prime is going to end up being 4V1 squared over 2G. And everyone's going to be like, oh, I'm going to sit there and nope, don't do that. Because this part here is the same as that. So what you're seeing is that your H prime equals 4 of your H. So your H prime is 1/4 of your H. So that's actually going to be greater than 2H. And a lot of people forget about that squared. Squared will catch you. That squared will get you. And now, okay, so part C. So block A and block B, both of mass M, are moved to a different frictionless track. So we're moving them to a different track. It's not going in the circle anymore. As shown above, let VA be the minimum initial speed of block A that allows block B to make it over the hump in the track. Block A is then replaced. Okay, so we're going to hold off on there. So we're stopping there. So we have the same mass, and it's hitting and going over. So again, this same mass situation is a perfect elastic collision, the same thing as up here. So if we sit here and did a momentum equation, we would have A of VA plus, and our block B is not moving, equals our block A would completely stop and be VA. So your velocity of the two blocks are going to have to be the same because it's the same mass. It's a complete transfer. So A would come and hit. As soon as it hits, all the momentum gets converted to or moved to block B. Block A stays still and block B continues at the same exact speed. So now block A is then replaced with a larger block, block C, which has mass of 2m as shown below. Block C makes a completely inelastic collision with block B so that they both stick together and travel along the track. What is the minimum initial speed? Oh, hold on. What was that? Minimum initial speed. So we already know that our minimum initial speed has to be VA. So what is the minimum initial speed, speed C, that block C must have so that the two block system makes it over the hump? So this was the first part of part C was a elastic collision. Now we're looking at an inelastic collision. So an inelastic collision. So we have mass C is moving at VC plus, again, block B is not moving, equals, but now our block mass C plus mass B times, and we're trying to figure out what this velocity is going to be. We're just going to call that a BC because it's the velocity that they're both moving together. And it wants our answer in VA, which we kind of solve that because the minimum initial speed. So let's kind of get like terms. And we could have gotten like terms here because it says that they're both mass M. So if we want to backtrack, VA equals, oh, look, they're the same. So I guess I should have showed that. But our MC is 2M VC equals 2M plus M V BC. So we can get 2M VC equals 3M V BC. So we got that far. Now, it says let VA be the minimum initial speed. So the minimum initial speed. So we're looking at the minimum initial speed. So our VBC is going to end up equaling our VA. Because it's wanting to know what minimum initial speed. So we can just plug in VA here. So 2mVC equals 3mVA. And this is tricky because it says a minimum initial speed. So it's kind of have to be like where there's like kind of repeating pattern of words to pay attention to that. So that stumped me too when I first was looking at this. I was like, oh, Lord have mercy, what's going on? And then it's because of that minimum initial speed, and now you're just solving for your VC because it's wanting what should your VC be in terms of A. So your masses end up canceling, so you're left with 2 VC equals 3 VA. You get VC by itself. You get VC equals 3 VA over 2. And I was looking at the AP key for this. The sad thing is you actually got no points for this part right there. So in this part, you got no points for this. No points were given for getting the right answer. You got points for you got points for showing all the work, but you got absolutely no points for doing the answer. They're not. It's very common that they don't give you any points for getting the right answer because they don't really care. If they believe they can get the steps, you can get the right answer. So you never just put the answer. You never just put the answer. So hopefully that shows like different types of free response, deriving, and paragraph forms. If you have any questions, please don't be afraid to ask. Have a good day. Bye.